quantum numbers. We are starting with the principal quantum number. Number which is given by the letter n, and n can have values 1, 2, 3, etc. Now the quantity that n quantizes, so quantum number is something that quantizes some quantity. So which quantity it quantizes? It quantizes energy, and how it is being quantized? Energy En is equal to minus 13.6 electron volt by n square. This is for hydrogen atom. Okay, so the principal quantum number n, which has the value 1, 2, 3, etc., quantizes energy, that is the quantity which quantizes quantized by the quantum number n, that is the principal quantum number, and this is the formula. And second quantum number is orbital angular momentum quantum number. Orbital angular momentum quantum number, and another name is azimuthal quantum number. Okay, now it is given by the letter L, and this orbital angular momentum quantum number quantizes the angular momentum. So it quantizes angular momentum and that is L, which is the angular momentum. And what are the values this L can have? L can have values from 0 to n minus 1. Suppose the n value is equal to 3, the L values are either 0, 1 or 2. So these are the possible values of L for n equal to 3. Okay, now corresponding to n equal to 3, there are different states for L. So this is 0, 1, 2, and corresponding to that we say that it is S state, P state, D state, etc. If it is if n equal to 3 or n equal to what you say, n equal to for 6 you have L equal to 0, 1, 2, 3, 4 and 5, and similarly those values corresponding states are S, P, D, F, G, H, again I, etc. there. And how does it quantize? L is equal to H cross times L into L plus 1. So this is how it quantizes, and L into L plus 1 under root. Yeah, so this is how angular momentum L is being quantized. Now we have the another quantum number, that is magnetic orbital angular momentum quantum number. Okay, and this, the letter is ML. It quantizes LZ quantizes z component of angular momentum. That is Lz. Okay. Now Lz is equal to ml times h cross, and what all this ml can have? Ml can have, for example, if L is equal to 3, ml can have values from -3, -2, -1, 0, 1, 2, 3. So from this value is from -L to +L. So these are the different values, and if if you have the orbital angular momentum quantum number L, then how many ml values are there? There will be 2L plus 1 ml values. So these many number of ml values will be there. For example, here we have 3, 2 into 3 plus 1, that is 7. So there are 7 ml values, -3 to +3. So how does it quantize? It quantizes Lz. This is L. Lz is equal to ml times h cross. Now fourth one is spin angular momentum quantum number. S quantizes the spin angular momentum S. So quantizes spin angular momentum. Momentum S. So this is small letter S, and this is S vector. So for S we have half. This is for electron. Electron is spin half. And how does it quantize? S is equal to the magnitude of S, basically h cross into root of S into S plus 1. So for S is equal to half, so it must be always equal to h cross into root of half times 3 by 2, which is equal to h cross by root 3 by 2. Now here we have the fifth one, that is magnetic spin angular momentum quantum number. So EMS quantize the value, this magnetic spin angular momentum quantum number is EMS, and it quantizes Z component of Z component of spin angular momentum. Okay. So what is that? So EMS quantizes SZ, which is a vector, and yes z is equal to ms times h cross. So ms values are either plus half or minus half. We know that s value can have only half values, so ms can have plus half or minus half. And how does it quantize? So this is the quantizing parameter, that is sz is equal to ms times h cross, that is nothing but h cross by 2. Now we have the total angular momentum quantum number. Total angular momentum quantum number, and that is given by j, and j equal to, so that is, actually it is small letter j, and you know that the total angular momentum j is equal to L plus S, and it quantizes, so j quantizes the total angular momentum j. And how does it quantize? So the magnitude of j is equal to h cross root of j into j plus 1. Okay, and what are the possible values of j? J is equal to, take the j value can be taken from L plus S, that is the magnitude, to L minus S. Just for example, if we have L value equal to 3 and S value equal to half, the J value can take values from L plus half to L minus half, so that is 3 plus half to 3 minus half, that is 5 by 2 to 3 by 2, sorry, 7 by 2 to 5 by 2. So 7 by 2 and 5 by 2 are the possible J values. Now we have the total magnetic angular momentum quantum number. Total magnetic angular momentum quantum number. So what does it do? It is given by mj, and mj quantizes z component of the total angular momentum quantum number j. So that is j, z component of j, which is equal to j z. So how does it quantize? So what are the possible values of mj? Mj values can go from minus j to plus j, and jz is equal to mj times h cross, and this is it. This is jz magnitude. We have discussed about magnetic orbital angular momentum quantum number and the magnetic spin angular momentum quantum number and the total magnetic angular momentum quantum number mj. Now coming to the degeneracy levels of each degeneracy, we have the degeneracy for this magnetic orbital angular momentum quantum number L is 2L plus 1, as we have discussed. So this is called L degeneracy. And coming to spin angular momentum quantum number, magnetic spin angular momentum quantum number, we have 2s plus 1, 2s plus 1, which will be always equal to 2 into half plus 1, that is equal to 2, and this is called S degeneracy. So L degeneracy is equal to 2L plus 1, S degeneracy is 2S plus 1, and the degeneracy, J degeneracy, is 2J plus 1. So 2J plus 1, that is J degeneracy. Now what about we mean by degeneracy? Degeneracy is two states or states with same energy. This is called degenerate states. Whichever states having same energy, they are called degenerate states. So for L, for example, L equal to 2, it will have 5 states with same energy levels. That is with respect to L degeneracy. Magnetic moment of electron. Now considering the orbital motion and the spin of the electron, we have two kinds of magnetic moment, that is orbital magnetic moment as well as spin magnetic moment. Orbital magnetic moment is mu L, this is mu S. Okay. So magnetic moment mu is equal to I cross A, that is the area, and I is the current, and mu L is given by minus GL E by 2m into L. So that is the magnetic moment mu L given by minus GL E by 2m into L, and the value of GL is equal to 1, and mu S is equal to minus GS E divided by 2m into S, and the value of GS is equal to 2. And similarly mu J, this becomes the total orbital magnetic moment, mu J, that's equal to minus GJ E by 2m into J, and GJ is equal to Landé G factor for total magnetic moment, and the value of Gj is given by Gj is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2 into J into J plus 1. So this is Gj, and there is a small note. This is about gyromagnetic ratio. ratio, that is mu L divided by L. So here also the magnitude and the magnitude, so that is GL times E divided by 2m. So that's, since GL is equal to 1, you have E divided by 2m, which is the gyromagnetic ratio, and again you have mu s by s, the magnitude, that's equal to GS E divided by 2m, and GS value is 2, so you have E by em. Okay, so the L, S and J, this is what we are going to see here. The angular momentum L, spin angular momentum S, and the total angular momentum J. So we are going to find out the angle between L, S and J. So let the angle between them represent by theta. So theta LS, so angle between L and S is given by J into J plus 1 minus L into L plus 1 minus S into S plus 1 divided by 2 into root of L into L plus 1 times S into S plus 1. The angle between theta, that is the theta of LJ, L and J, which is J into J plus 1 plus L into L plus 1 minus S into S plus 1 divided by 2 times root of J into J plus 1 divided by L into L plus 1. The theta Sj, which is equal to J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by root of 2 times root of J into J plus 1 times S into S plus 1. Discussing the coupling schemes, let us start with LL coupling. This indicates that there are two electrons. One electron is in state L1 and the second electron in the state L2. This is vector representing the L1, this is L2, and this is processing over the net value of L. So now we get the coupling scheme, that is the L as L1 plus L2, and what are the values of the values this L can have? L can have values from L1 plus L2 to L1 minus L2, both are magnitude. And so this is LL coupling. to S coupling, S coupling, we have here the S1, this is S2, both are processing in the net vector S. So the vector S is S1 plus S2, and what the values that S can have. So here also there are two electrons, electron with the spin half. So S is equal to half, that is S1 equal to half and S2 equal to half. So what are the values S can have? This particular S can have values from S1 plus S2 to S1 minus S2. So S1 plus S2 is half plus half, so that is 1, and this is 0, S1 minus S2. So S is equal to 0 and 1. So this 1 is called multiplicity is given by 2S plus 1. So S with multiplicity 2S was plus 1 gives 3. So this is called a triplet state, and the spin 0, the net spin equal to 0 implies it is 2S plus 1 value is equal to 1. So this is called singlet state. So two electrons, if the electrons are even, it will produce odd multiplicity, while if the electrons are odd, it will create even multiplicity. So since here we have two electrons which are even, it is producing odd multiplicity, that is singlet and triplet. If the electron was 3, there were 3 electrons, 2s plus 1 will come to 2s, that is half plus 1, 2 or 3, so it will give you even multiplicity. So let us note that point here. The number of electrons are odd, then you will have spin is equal to half, 3 by 2, 5 by 2, etc. up to n by 2. Now if the number of electrons are even, then spin will go in this way: 0, 1, 2, 3, etc. up to n by 2. Okay. And finally we have the LS coupling. LS coupling, it represents the L, the orbital angular momentum, and the spin angular momentum coupling. And here we deal with, this is J, this is S, and this is L. So J is equal to the vector L plus the vector S, and both L and S will precess over the vector J. Now this J is equal to L plus S. Okay. Now coming to the values of the values that j can have, that is j values are from L plus S to L minus S. Okay. Now just for an example, we will consider P D. Now this represent one electron is in, so one electron in P and one electron in D. So P and D. So we have already seen that the spin is equal to half plus half or half minus half, which will be equal to 1 or 0. Now coming to the L1, that is the angular momentum for the first electron, that is it is in P state, right? So L1 equal to 1, and L2, the second electron is in D state, so L2 will be equal to 2. So what are the possible values of L? So what possible values of L are L1 plus L2 to L1 minus L2. So now here we know that it is L1 plus L2 is 3 to 1, so which includes we'll write it in increasing order, 1, 2 and 3, and the S values are 0 and 1. So this is S, this is L. So L equal to 1, 2, 3 and S is equal to 0 and 1. Now let us write down the number of J values. For that let us draw a table here. So here we will write L, and on the this side column we will write the spin. So we will start with 0 and 1. 0 is a singlet state, 1 is a triplet state, and L values are 1, 2 and 3. 1 represent the P state, 2 represent the F state, and 3 represent the D state. So with 0, 1 we will have 0 plus 1 and 0 minus 1, so there is only 1. So 0, 2 it is 2, 0, 3 it is 3. Now 1 and 1, it is 1 minus 1 is 0, 0, 2, 1 plus 1 is 2, so 0, 1 and 2. Similarly here you will have 1 and 2, so it is 1, 2 and 3. It is 1 and 3, it is 2, 3 and 4. Okay. Now what are the spectral terms that we have is, this is 1, this is singlet P state with J value 1. So how do you before going to that, we will represent the spectral term by L, J, 2S plus 1, which is the multiplicity. So multiplicity here is 1, that is the singlet. This is P value is, J value is 1. This is one of the states, spectral state or spectral term. Now this is 1, F, 2, then again another singlet 1. So okay, P, this is D, okay, and this is D and this is F. Please kindly make the change here. So P, D and F. So this is D, this is F. So 1F, 3. Now these are the singlet state. Now we have the triplet state. Triplet state starts from 3, and P. What are the things? 0, 3p1 and 3p2. Now we have D. Again it's a triplet state. 3d1, 3d2, 3d3. Coming to the F state, 3f2, 3f3, 3f4. Now here we together we get 12 states. So 12 states or 12 spectral terms. How to get the number of spectral term? So number of spectral term here is 12. This is spectral term. Now how to get the number of spectral term even before doing this finding all these values? It is nothing but 2 into number of S values into number of L values. Okay, here we have 2 into S values. There are 2 S values into how many L values? There are 3 L values. So 2 into 3 into 2, that is equal to 12. Here we are discussing the spectral term. Now the notation of the spectral term is represented as L. This is 2s plus 1 and here you have J. Now 2s plus 1 gives the S coupling. Then here you have L, which gives you LL coupling, and the J represent LS coupling. Okay. Now to understand this, let us take an example of 2 electrons, one in P and another in D. So P and D state. So since the electron S1, one of the electron is half, the spin is half, S2 is also half, the net spin is equal to S1 minus S2, the magnitude of S1 minus S2 to S1 plus S2. So it gives you S1 minus S2 is half minus half, that is 0, to half plus half, that is 1. So 0 to 1, and now S is 0 and 1, so you have either 0 or 1. So 2s plus 1 is the multiplicity, the term is called multiplicity, and when you apply S is equal to 0 here, you get multiplicity equal to 1, and when you apply S is equal to 1 here, you get multiplicity equal to 3. Now 1 and 3, this is called singlet state, and this is called triplet state. Triplet. Now coming to the LL coupling, one of the electron is in P state, so L1 equal to P and L2 equal to D. Okay, so L1 equal to P means the value is 1, L2 equal to D means value is 2. So L value is equal to L1 minus L2 to L1 plus L2. So this gives L1 minus L2, that is 1 minus 2 to 1 plus 2. So 1 minus 2 is 1, 2, 3. So 1, 2 and 3. So L values are 1, 2 and 3, which represent the one is P, 2 means D, 3 means F. Now here S will have singlet and triplet state. So you will get singlet and triplet states of P, D, F. Now let us see how we can do the LS coupling. We have to consider the L and S coupling, which is nothing but J. So here you have S and here you have L. Now this gives 2S plus 1, that is the singlet state for 0, and here you have triplet state for 1, and L values are 0, 1, 2 and 3. So 1 represent the P state, 2 represent the D state, and 3 represent the F state. So 1 P means 0. Write 1, 2 and 3, 0, 1. So 0 and 1 you have 1, 0, 2 it is 2, 0, 3 it is 3. Now 1, 1 it is 1 plus 1 is 2, 1 minus 1 is 0, so it will be 0, 1, 2. Okay. Now 1 and 2 gives you 2 minus 1 is 1 and 2 plus 1 is 3. So 1, 2 and 3, all 3 states will be there. Here you have 3 minus 1, 2, 2, 2, 3 plus 1 is 4. So 2, 3 and 4. Okay. Now what are the states? The states are, first one P, 1, here you need to write 2s plus 1, right? 2s plus 1, here it is 1, 2s plus 1 value is 1, and here it is 3. So I am writing the first one here, P, that is 1, so 1 P. Now you need LS, LS is here 1. Then you have D, D again it is 1, but here you have 2. Okay. Now F, again 1, this is 3. Now you can say the singlet state of P, D and F with LS coupling 1, 2 and 3. Now coming to the triplet states means you will have 3 values of states. See, you have 3 values of each states. So starting with P, so it is a triplet state. You have P0, 3P1 and 3P2. Similarly for D, it is a triplet state, 1, 3D2 and 3D3. Again for F, triplet state, F2, 3F3, 3F4. So there are 3 singlet states and 9 triplet states. Together you have 12 states. ground state spectral term. The ground state spectral term is given by Hund's rule. As you know, this notation for the spectral term is L, 2s plus 1 and J. There are few conditions for the finding out the ground state spectral term using the Hund's rule. Now with respect to the spin, we have to understand is higher the multiplicity, lower will be the energy. Higher the multiplicity, lower will be the energy. The energy. Now here is a question: what if the multiplicity is same? If S is same, what will happen? For example, if you have 3p0, 3p1 and 3p2, so which one of the given spectral terms is the ground state spectral term? Now then comes the rule for the L state, that is higher the L value, lower is the energy. So higher the L value, lower is the state, lower will be the energy. Now what will happen if the L values are same? One example we can assume is 3p0, 3p1, 3p2, and in the D state we have 3d1, 3d2 and 3d3. Now here we see that L values are same, so here we have the condition that higher the L value, lower is the energy. So somewhere here 3d1, 3d2 or 3d3 is the answer. Now in this 3d1, 3d2 or 3d3, which is the correct answer? We will find out it is using the rule, that is we have to consider the atoms. Now if it is less than half filled, so less than half filled, if it is less than half filled, if the electrons are less than the half filled of that particular state, then you will go for lower J value, or if it is more than half filled, you will go with higher J value. Now let us take an example of PD configuration. Now this PD configuration states that one electron in P state and another one electron in D state, so P and D. Now what the spectral terms are. Spectral terms are, as we discussed before, we have the table something like this, where you get the S and the L. L is coupling with this P, D and F, and the states are singlet and the triplet state. So P, this is singlet 1, this is 3. So 1, this is 1, 2 and 3. So 1 1 1 and 0, that is 1 2 and 3. Here you have 0 1 2, this is 1 2 3 and 2 3 4. Now what are these states? We starting with, so the spectral terms are starting with P. We have 1 P1, then 1 D2, 1 F3. Okay, then you have triplet states, 3 P0, 3 P1, 3 P2. So then 3 D1, 3 D2, 3 D3, then you have 3 EF2, 3 F3, 3 F4. So these are the spectral terms. Now we need to apply the Hund's rule and find out which state is having the lowest energy. So the first one is regarding the S. Higher the S value, lower is the energy. So S value is higher here. Here you will have the lowest energies. Okay. Now so here is where we are going to have the lowest energies. So second state is regarding the L. So here also we have the same rule, that is higher the L value, lower is the energy. So L value is higher here. So out of these three, you have one of the state as the lowest energy states. Again, the spectral terms, the ground state is highest energy is 2, that is 3 F2 is the highest energy. So then 3 F3, 3 F4, then you have 3D1, 3D1, then 3D2, then 3D3, then you have 3P0, 3P1, 3P2. Then again we have the singlet state. Now here starts with F. So 1 F, 1 F3, then 1 D2, then 1 P1. So this is the highest state energy, this is the lowest energy state. the spectral term. We are dealing with the spectral terms now. The first case is when we have non-equivalent electrons. Which means both the electrons are in different states. Electrons in different states. So when electrons are in different state, for example P-D, as we have just discussed about, or something D, F. Okay, so these are examples of non-equivalent electrons. The method that we are going to adopt is ELS coupling to find out the spectral terms or the ground state spectral term. Okay, so ELS coupling is the method that we already know. We have to find out the S values, and similarly we will find out the L values. Then we will find out the J, which is equal to EL plus S, and the values are from L plus S to EL minus S. Okay. Now through this ELS coupling, we have also seen that we can find out the total degeneracy. Then the total atomic degeneracy is given by sum over J, taking all the J values into consideration, 2J plus 1. Okay. Now if the one way is to find out it using the ELS coupling method with the table that we have drawn a few minutes ago, or you can also use directly from for example, our one is in D and another is in P state. Okay, one electron is in D and P or PD. Now how many electrons are available, or these positions or the states are available in D? D is 2 and this is 1, right? So here it is 2L plus 1. So 2L plus 1, if you put L equal to 2, you will get 5. And similarly for this is for D, and for P, 2L plus 1 value will give you 3. That means 3 cells are there, orbitals. So 5 orbitals, and here you have 3 orbitals. This is 1, 2, 3, 4, 5. 1, 2, 3. Now in this we will have 10 electrons. In this we can occupy 6 electrons. So one of the each positions are occupied. So one would be like this, Okay. Now each of these orbitals can occupy 2 electrons due to pairing. Okay, now 10 and 6. Now how to find out the total degeneracy? You can do 6 C1 combination times 10 C1. That means out of 6, 1 is being occupied. Out of 10, 1 of the position is being occupied. So this gives you 6 times 10, which is 60. Now what is NCR? It's equal to n factorial divided by n minus r factorial into r factorial. Okay, so that gives you 60, and again, yet the total degeneracy is given by sum over j into j plus 1, sorry, 2j plus 1, 2j plus 1, and this will be equal to product of two NCRs, right? So product of NCR, where n is the number of electrons possible in the given state, and r is the number of electrons present in the state. Pi represent the product of. For equivalent electrons, we will follow the same method, that is the LS coupling, but with the small changes. The LS coupling is used now. The equivalent electrons are, some examples are P2, S2, then D2, etc. We are dealing with only 2 electrons. Okay, so now consider some P2, that means the 2 electrons are in P state. So the electron spin S1 is equal to half and S2 is equal to half. So the net S value will be either 0 or 1. Coming to the L, the angular momentum L1 equal to P, that is 1, that L2 equal to again P, that is 1. So L values will be, capital L values will be from 1 minus 1, that is 0, 1 plus 1, that is 2. So 0, 1 and 2. Now 0 represent S, 1 P and 2D, right? So making the table for the LS coupling, this is S, L, so 0, 1, 0, 1, 2. Okay, now this is S, P and D. Now this is the singlet state. Starting with singlet state, we have 1. Singlet state means it is 1, this is 3. So 1, the L is S, 1 is 1, oh sorry, 1 is 0, and here you will have 1P, 1P1, here you have 1D2, and for the triplet state we will write like this, that is triplet S 0, then triplet 0. Okay, so 0, 1 and 0, that is here. There are sorry, wait a minute, that is 1 is 1, then 1 and 1, so 1, 0, 1, 2, so 3 P 0, 1, 2, and here it is 3 D 1 and 2, that is 1, 2, 3. Now what you have to remember, for the same equivalent electrons which are in the same this thing, that is the state, we have a condition that for the singlet state, the L should be even. L should be even, and for the triplet state, L should be odd. Now coming back to this coming back to the LS coupling scheme, according to the condition that for singlet state L should be even, so this is the singlet state and L has to be even, so only there and here, so this is not important, okay, it does not exist. And for the triplet state, L should be odd, so this is the triplet state and L has to be odd, only odd is 1, so only this will be there, okay, this is not there, okay, yeah. So what I will put around for which all possible states, so this is also possible state, so the possible states are 1 S0, 1 D2, then 3P0, 3P1 and 3P2. So these are the possible spectral terms for equivalent electrons from P and D. Sorry, equivalent electrons from P. Now here we are going to find a shortcut method to find the ground state spectral term. One example is F6, that means we have F is the orbit, and this 6 is the number of electrons present. So F, so this is how you can draw the F orbital or the state, 1 2 3 4 and one more. So for F there are 7 orbitals, and in each orbital we will have 2 electrons present. Now we have to arrange 6 electrons, so 1 2 3 4 5 and 6, and after once it is completed, we will start pairing it. So since there are only 6, now how many it can occupy? It can occupy 14 electrons because there are 7 orbitals, okay. So out of this 14, only 6 are being. Now we need to find out the spin as well as the angular moment, okay. So this is spin value half, so since it is electron, everywhere you can put half. Now corresponding L values, we have to start giving the L values, so it starts from 0. So here you have -1, -2, -3, and this is 1 2 and 3, so it starts from -3 to plus 3, right? L value, we will write S P T F, right? 0 1 2 and 3, and for that n value should be equal to 4. Okay. That is the principal quantum number. Now it starts from -3 to +3. Now what we have to do is we have to add this S and L. So all spin half, it get added to 6 times the half, that is 3. Now L is wherever there is electron, you have to count that. So -3, -2, -1, 0, 1, 2. So up to here we have seen. So the L value is 3. Now you can take the magnitude of this after adding all. Okay, so 3 and 3. So we can write S is equal to 3 and L equal to 3. Now we need the ground state spectral term. So this is the last step. 2s plus 1. What is 2s plus 1? Spin is 3, so 2 times 3 plus 1, that's equal to 7. Okay, now we got the multiplicity, that is 2s plus 1. Now L value is equal to 3, which gives us the L as F, that is in the F state. Now what is J? J equal to, what should be the J value? What are the possible values of J? J possible values are L plus S to L minus S. So that what is L minus S? 3 minus 3, 0, and 3 plus 3 is 6. So 0, 1, 2, 3, 4, 5, 6. So J is equal to 0, 1, 2, 3, 4, 5 and 6. Now we need to know one thing, whether J is half filled. We have to use either half filled or more than half filled. This is less than half filled or more than half filled. Now look at the orbitals. This is half, less than half filled. Up to here if you use, it is half, and if it started pairing, it is more than half filled. Okay, so it is less than half filled. If less than half filled, we have to use lower number, lower J value. So lower J value is 0, so we will go with 0. So multiplicity is 7. The orbital, the L value is F and J value is 0. So this is the ground state spectral term without doing the all LS coupling scheme with 3 set of S values. We can find the spectral form directly by using this method. Now this is also important to understand how to find out the configuration. Electronic orbits of configuration of electronic orbits. So this is what we have learnt in the lower classes chemistry. 1 S, 2 SP, 3 SPD, 4 SPDF, then 5 you have SPDF, G. And how do you do this? Start with the S, then you go with ESP. So this is PS, ESPD, and it moves on, right? Yeah. So how we are going to arrange? So instead of going to in this way, directly you can remember it this way. Yes, yes. So we have already counted yes and yes from 1 and 2. Now PS, right? Now we have DPS and DPS. Now if you want to write the what is that F SPDF, so F DPS. So this with the first orbit, second. So start numbering with in increasing order wherever you see the yes. So this 6 and this is 7. Now P, we know that it will start from 2, so it is 2. This is 3. Here you have 4, 5 and 6. Now we know that D will start from 3, so it is 3. This is again 3. This is 4, sorry, it is 3, 4, 5. Okay. So this is how you will find the electronic configuration. For example, if we are asked to find out the aluminum 13, so what you have to do is you have to arrange this 13 electron in these orbits. So 2 2 arranging the aluminum So arranging this aluminum has got 13 electrons, so I am placing 2 here, 2. Now rest we have 9 more electrons to be placed. In P you can place 6, then you have to go with S. Again I have placed 1 more, then 3P. What is left? Only 1 more is left, so 3P1. So 3P1. Now it is P1. Now P1 means out of this 3 orbitals SP, you have only 1 electron here. Now you find out the S value and L value accordingly. This is 1/2. It starts from 0. This is -1. This is 1. So -1. So S is equal to half, L equal to 1. So this is how you start doing the coupling schemes. Okay, so L plus S to L minus S, L plus S to L minus S. So 1 plus half, that is 3/2. 1 minus half is half, so half and 3/2 are the J values. Now since it is less than half filled, we will go with lower J value, that is half. So what is the L value? L is 1. And what is this multiplicity? 2s plus 1. So 2s plus 1 gives me 2 into half plus 1, that is 1. So it is a singlet state, so singlet. L is 1, so SP, so P. And what is the J value? J value is half, so this is the spectral term. 1P half is the spectral term. So this is how you can find out the spectral term of any atom.